and we can move that throttle up to max power.
Over 50,000 horsepower, that's massive.
Just go careful, Sam, the leading edges are pretty sharp.
Test cell, which is a building within a building.
Wow. We can do water ingestion testing.
This is our Dreamfix facility.
What went wrong with the Dreamliner?
A special Trent 1000 over here.
Wow, this is a very different one.
Once it's finished, this will be the world's largest indoor test bed for experimental testing.
It's like a swimming pool.
Yeah, so this isn't actually a swimming pool.
I was really impressed, but this is really geared up for the future generation of the engine, like the Ultrafan. Welcome to Derby in the UK. When you think about Rolls Royce, you probably think about their cars, Rolls Royce Phantom, Rolls Royce Ghost. But for Afghan like me and many of you, we love airplanes. We know Rolls Royce make great airplane engine. Today we're going to take a look inside the Rolls Royce engine factory. This building's like huge. Looking through what they've done, to me, it's like rocket science. But here it's just production. Every 20 days, a new engine gets produced.
Welcome, Sam, to our production test facility. This is where we start to build the engines. So today we're going to look at engine build for a XWB engine, which is the exclusive engine on the A350. Start of the process really here. We've got behind us a fan disc. So this is where the fan blades go. If you look over behind the fan disc, you can see where the blades come in. So they're manufactured and brought into here. So we've got fan blades, fan disc, and over on the table here are the Annulus Fillers. Now they're the pieces that go between the blades to make a nice smooth finish for the air flowing into the engine. So this really is the start of the process for our XWB engine. So what we've got here now is we brought the disc, the blades and the Annulus Fillers together and formed the fan that goes at the front of the engine, where the flow goes through the engine and it's the fan that produces the majority of the thrust for the engine. And this is an assembled fan for an XWB engine.
Wow, look at this blade here.
Just go careful, Sam, the leading edges are pretty sharp. And that's to get a really efficient flow into the engine. We've just seen the fan at the front of the engine. What we're looking at now is a turbine and a shaft that goes to the back of the engine. Now what this is what drives the fan or the compressor round. So you tend to see turbine blades hidden in this casing up here, and then a long shaft that goes through the middle of the engine and drives the compressor or the fan at the front. So this is another module on build that comes together to make our XWB engine. What we've got here now is the low pressure turbine at the back of the engine. That's the start of the core build, so that's right at the back of the engine. We put that vertically and gradually build that up in what we call a stack. That's building the core, and then on the other side of the shop, over here, we've got the fan being built. We saw the fan blades being built next door. This is the fan case, and you can see lots of pipes and wires on the outside, very complex build process. And you can see we use electronic models to direct the guys that are building the engine. So they'll look on the screen, look at where the pipes need to go, check that before they go and actually put them on the engine. So this is where we build the core of the engine. So what we do there is we start with the compressor at the bottom, build up to the combustor, and then the turbines on the top. And as you can see, the different levels where the guys that are working on the engine need to be close to the bit they're working on, so the floor moves as the engine build progresses. Behind me the core is finished build now. So it's now ready to marry with the fans. Remember, the fan and the core were built separately. Here's the final core ready to go. We just need to join it to the fan. And if you look behind me here, you can see the core has been flipped to be from vertical to being horizontal, and the big fan case has been put on the front.
Bill, what's this machine's been doing, spinning around?
Okay, well before we put the fan blades in the fan case, we need to make sure that the fan blades are a perfect fit to the fan case. We don't want a very big gap between the fan case and the blades. So this is just checking that and making sure that they're going to fit perfectly together.
Behind the 22 giant fan blade is the turbine blade inside. They can generate, each of them, 800 horsepower. So together, 68 turbine blade generate over 50,000 horsepower. That's massive. This looks like the engine's ready to roll.
Just 20 days from start to finish, and the engine's ready to go across the test before it goes to our customer. So let's go over now and look at our test facility.
Test facility. So
Yep.
the engine go to test facility now.
That's right, that's
Then
where we
let's
go
go.
next. Let's
Yeah.
go.
Welcome to 58-bed control room. Here is where the guys take control of the engine, whether it's to gather data or ensure build conformity. We take the engine, we rig it to the test facility, and we carry out the customer's requirements, either to test it for maturity, for different strains, pressures, temperatures. We can do many things here in Derby in the test bed. This is basically the pilot takes control of the engine with the throttle, and we can move that throttle up to max power. And that will then put the engine in a certain mode through the power range. We gather the data, we write everything we do electronically and record everything we do, and we also look at real-time data in the control room to ensure we are getting the customer's requirements. So we have a safety system here in the test facility which allows us to make sure that we have all the people and the personnel out of the test facility before we start work in rotating the engine. So every single system has a lock on. Until all those locks are in place, we cannot start the engine. It's an interlock system for safety. So here we are entering the test cell, which is a building within a building, which makes the building extremely quiet when we run the engine. This is the test cell now. So when we go through this door, we'll go into the test cell and we'll be able to look at the test facility.
Wow.
This is where we do different types of testing. We can do pass-off testing before engines go to the customer. We can do research testing or development testing. Some of the really interesting, exciting tests we do that we don't do very often, that we do in development, ready for certification, could be fan blade off tests, where we blow a fan off and check that it's contained within the system. We could do
you have to destroy it, blow it,
destroy a blade
how they
to
can
show,
sustain that.
to
Yeah.
just prove that should that happen in service, very unlikely that it would, but we've got to prove that that event is safe, so we do that. We can do water ingestion testing. We pour loads of water down the front of the engine to simulate a storm and flying through a storm and show that the engine performs correctly in that. We can do bird strike testing, where we fire birds at the engine to simulate what could happen if you were to hit a bird and show that the engine's strong enough to take that. And we can also do what we call cold start testing, where we basically bring a massive fridge in and put the engine in it.
Make it really cold.
Overnight, make it really, really cold, and then take the fridge away and prove that we can start it cold, because engines find it more difficult to start in really cold conditions. So all kinds of really important testing that we can do on this cell in Derby.
Right.
So should we go now and look at the preparation shop where we get the engines ready before they go onto the test bed? Okay, so we're entering our prep shop, our preparation shop, where the engines come before they go on the test bed. Now every engine that we build here in Derby will come through here before it gets delivered to our customer. So a relatively simple set of checks that we do on the test bed just to make sure everything's working properly. Very similar to what you might get with a car. So when somebody builds a car, before they deliver it to the car showroom, they just give it a quick drive just to make sure everything's functioning correctly. We put the white inlet on the front, which simulates, it's different to what would go on in service, but it simulates the front of the engine. We connect it up to this sort of carriage at the top, which simulates the pylon, the bit that attaches the engine to the aircraft. It's not exactly the same, but it represents it. And then you can see lots and lots and lots of connections. So the data then comes from the engine into the pylon connects together in the test cell, and all that data flows back to those computers that we saw in the control rooms, so the engineers and the test engineers can understand how the engine's performing.
So Sam, this is our DreamFix facility, which is a physical representation, if you like, of the effort we're putting in to fix this problem we've got with the Trent 1000 and reduce the disruption for our customers, which we're really regretful of. At the moment, we've got about 4 engines in here, which we're fixing quickly on a turn time to get them back out into the fleet. And you can see it around you, the activity in here to really start to get onto this problem and crack it with embody all the fixes that we know we've got designs for now.
The Trent 1000 engine is developed specially for 787 Dreamliners, but somehow they suffer a problem. What went wrong with the Dreamliner on the Trent 1000 engine, Richard?
Well, we had three issues, but I think the easiest way to try and understand it is use a car analogy. Imagine you've got a car, it's been proven safe for use, but you know that the tyres will wear out at some point, you know that the windscreen wipers will wear out at some point. Those things happen and you bring those in to fix them as and when they need. 2 of our problems were like that. So we had an HP turbine and IP turbine that were wearing out slightly earlier than expected, so you bring them in to replace them earlier than expected. On top of that, and the third problem which made it a bit trickier, was we had an IP compressor problem, which was not something that you can monitor on condition. So it's not like wearing your tyres out or looking at your windscreen wipers. Imagine you had a problem with an oil pump that you had to bring in. If you bring that car in because the tyres you know have worn out, you don't necessarily replace the wiper blades and the oil pump at the same time. That's why it's taken a while for us to flow all of these fixes in, just because you don't necessarily fix everything at once. The engine's perfectly safe and perfectly reliable, it's just that we're not making it last as long as we and our customers would like it to. So that's the 3 problems we're addressing. So imagine you're bringing in your tyres, we're putting new tyres on, not necessarily changing the windscreen wipers at the same time because they might still be good to go. Then you come in next time, you change the windscreen wipers, your tyres are still fine. That's why it takes a long time, but we'll get there and we'll fix this problem. It's already, the design fixes are already in place. So Sam, we're in the DreamFix facility looking at Trent 1000s, and we've actually got a special Trent 1000 over here that's got some of our newer technology for future engines on, which I could like to show you if you want to walk this way.
Let's take a look. Wow, this is a very different one. This one has blue turquoise color engine blade. It looks like carbon, rim here. Yeah, so what's the latest technology breakthrough at Rolls Royce?
So this is actually a test engine for our latest carbon titanium fan and containment system, which is the application of carbon technology to reduce the weight of the front of the engine, the fan and the fan case. It's running on a Trent 1000 donor engine because it happens to be the right size, but we've been putting this engine and the new system through its paces. This technology, it's taken a while for us to surpass our own class-leading titanium blades, and that's fundamentally because first and second generation carbon blades, while they were good for weight, they weren't as good for aerodynamics, whereas our titanium blades that we saw on the Trent 1000, they're excellent for both. Now, we've got a technology where, because of the 3D weave of the carbon fibre, we can make a blade that is both lightweight and aerodynamically efficient. So a system like this, at this size, would save about 750 pounds per engine, which is about, obviously on a twin-engined aircraft, 1,500 pounds of weight that you can really either burn less fuel or take more passengers. Because what we'll also do during certification testing is we'll put an explosive bolt into the root here and explode that when the engine's at full power, and then the engine has to prove it can contain the kinetic energy of that blade. If one of these were to let go in those circumstances, the amount of energy that we're talking about containing would be similar to if you take a BMW 3 Series and drive it off a 100-foot cliff. That's the amount of energy that this has to contain. And what we've got to prove as the engine manufacturer is that the engine doesn't necessarily have to continue running and producing thrust, but it does have to make sure that it runs down safely and no high energy debris penetrates the casing to go and harm the fuselage. So if one of this were to happen while you're flying, then you might spill your gin and tonic, but you'd be perfectly safe.
So today we're changing up to construction gear, because today we're going to see something under the construction.
So we're here today at Bed 80. So once it's finished, this will be the world's largest indoor test bed for experimental testing. So this is where we'll actually push our engines to their ultimate limits so we can understand how they really perform. So what we're doing now is really putting the intelligence into the building. We're fitting out the systems which will allow us to control the engine, but more importantly, understand what the engine's doing. And we can actually read up to 10,000 parameters on this bed. And we can take that data real time and we can actually stream it back out to the cloud so that it can actually link real time to all our various models. So really exciting for us. It's not just a construction project, you know, this is about testing for the future for Rolls Royce. We're now inside what we call the prep shop. So this is where we bring what essentially is a built experimental engine, but we now bring it in here to get it ready for test. So this is where we put the engine on a pylon, so effectively we make the engine think it's fitted to an aircraft. So that's the reason for the size of this building, is to allow us to actually manoeuvre the engines and get them ready. And with UltraFan, clearly one of the largest engines we've done, particularly in terms of its fan size.
That's huge. Yesterday I was in testbed 58. I was really impressed. But this is really geared up for the future generation of the engine, like the UltraFan, much bigger and much stronger capability.
That's correct. I mean, this is a lot bigger, but again, bigger for a reason. The UltraFan, the fan size is significantly larger. We will be putting a lot more slow-moving air through this test bed. So again, this is all about getting a smooth flow of air into that engine. And we can do big, absolutely we can do UltraFan, and clearly we've designed it to do a little bit more. But the important thing is we can also do small in this bed as well, so we can also go down to much smaller engines. It will basically be able to do every engine we make today and every engine we're intending to make in the future at this point in time.
It's like a swimming pool.
Yeah, so this isn't actually a swimming pool. So what this is about, we have a floor in here, and when we're testing, the floor's down flat. But when we want to get to the engine, because it's raised to such a height, what this allows us to do is we lift the entire floor up to the engine, and it's allow us to work on the engine while it's in the test bed, and then we lower it back down again. But yeah, absolutely, you can imagine people do come in thinking, what's that for? But yeah, no, it's a floor which comes up and down. We've moved from the test cell, we're now into the first section of the tube, which is where we start to manage the air coming out of the engine. Anyone who's been at the airport, you know what the noise is like, and I think lots of people have probably seen the videos on YouTube of people standing at the airport fences and seeing the power of the engine as it takes off. Clearly we need to make sure that we do something about all that power, and that's what this is doing. So this is about a 5.5 metre section tube, which has actually been designed to allow us to slow that air down as it comes out the back of the engine. Again, so by the time it actually leaves the test cell, people won't even realise the engine's running. This is effectively where the air will leave the test bed, and yeah, when we look at this, we call it the basket for obvious reasons. So this is where the air has come out of the engine, it's come through the big tube we've seen, it comes into here, which is an 8 metre section. And what we're doing here is the air is coming down, it's hitting that, what does look like the front of an engine, it's hitting that cone, but what that cone's then doing is it's spreading the air out throughout this space. And again, the idea is we spread the air out, we change its direction, we slow it down, and then the air can then all lift up. This test bed, you know, build a test bed like this probably every 10 to 15 years. So from an engineer's point of view, this really is a once in a lifetime opportunity. So we've got people working on this who are very, very excited because they know they're doing something for the future generations. And they know they may not get the opportunity again in their careers. Really exciting.
And their legacy will last for a lifetime.
That's it, absolutely.
Many more years to come
yeah.
with such an engineering feat like this.
Yeah, absolutely.